There is a place at the bottom of the Philippine Sea. The water above it weighs more than your body was designed to comprehend. You cannot see it from any coastline. You cannot feel it from any ship. The surface of the ocean above it looks like any other stretch of open Pacific. Blue, restless, entirely ordinary. Nothing about standing on a vessel in that part of the world would tell you the truth. 11 kilometers below your feet, the seafloor sits in a darkness so total. The pressure there is so enormous that ordinary experience stops applying. No light has ever reached there. No warmth from the sun. Nothing from the world above makes it down intact, except the weight of the water itself. That place has a name. It is called the Galathea Deep. Spending time understanding, it turns out to be one of the stranger journeys available. Really understanding it, from the physics to the organisms to what it means for the planet above. It is one of the more quietly wonderful journeys available to anyone curious about the world. Before we go any further, I want to ask you something simple. Where are you right now? What does the room around you feel like? Maybe it is late. Maybe there is a lamp on nearby, or the blue light of a screen. Maybe the temperature is comfortable in that way that only registers when you stop to notice it. The ambient warmth of a room that is just right. The weight of something soft around you. Whatever it is, whatever the particular texture of your surroundings at this moment, I want you to hold it for just a second, because where we are going tonight is as far from that room as you can get, while remaining on the surface of this planet. The Galathea Deep sits at approximately 10,540 meters below the surface of the Philippine Sea. It is the deepest confirmed point of the Philippine Trench, a long, narrow depression in the ocean floor. It curves roughly 1,320 kilometers along the eastern edge of the Philippine archipelago. It is not the deepest point on Earth. That distinction belongs to the Challenger Deep in the Mariana Trench, about 400 meters deeper. But depth records are not really the point of what we are about to explore. The point is what this place actually is, what it takes to reach it, what it does to everything it touches, what lives there and how and why any of it connects to things happening in the world above, including in ways that turn out to be genuinely important to the people living on the Philippine Islands, and to the chemistry of the atmosphere everyone on Earth breathes. The name comes from a ship. The HDMS Galathea was a Danish research vessel. It set out from Copenhagen in 1950 on a voyage that would take it around the entire world. Over the following 2 years, the expedition was not looking for headlines. It was not trying to claim records. It was simply trying to measure the ocean, carefully, systematically, with new instruments, in ways that had not been possible before. The scientists on board were working with technology sharpened by the Second World War. Echo sounding equipment, originally developed to hunt submarines, now pointed downward toward the seafloor. Pressure instruments, originally built for naval applications, now measuring the deep. When repeated measurements in the Philippine Sea returned depths consistently above 10,000 meters, the scientists did what good scientists always do. They verified them again, with different instruments, against adjacent depth profiles, with explicit documentation of every calibration procedure. The confirmation was careful. The numbers held, and the trench took the name of the ship that found it. Welcome to Info Jungle. If you enjoy calm, thoughtful documentaries about the natural world, consider subscribing. These videos are created to help you relax while learning at a gentle pace. 10,540 meters. If you have ever looked out the window of a long-haul flight, you know roughly how far that is. A Boeing 787 cruises at about 10,700 meters altitude. The distance between your feet and the ground below that window is almost exactly the same as the distance between the ocean surface and the floor of the Galathea Deep. Except that instead of clouds and open sky above you, you would be looking up through 11 kilometers of cold, dark, increasingly dense seawater. Or consider Everest. The peak of Mount Everest sits at 8,849 meters above sea level, the tallest mountain on the planet. If you placed Everest at the bottom of the Galathea Deep and stood on its summit, you would still be more than 1,600 meters below the ocean surface. The world's tallest mountain would vanish entirely into this trench, and there would still be water above it. These comparisons are useful for a moment, and then they stop being enough, because neither of them captures the most important thing about this depth, which is not the distance, but what that distance of water creates. Every 10 meters of water adds roughly the weight of another atmosphere pressing inward. At the surface, you are carrying one atmosphere, the weight of all the air above Earth, arriving equally from every direction. You have lived with it your entire life without feeling it. Your body is so perfectly calibrated to it that it registers nothing. It is simply the condition of existence. At the Galathea floor, that number becomes 1,100 atmospheres. Not 11, not 100, 1,100. The closest way to feel the scale of that might be to imagine the full weight of Earth's entire atmosphere pressing against you. Then imagine 1,000 of those, arriving simultaneously, perfectly equally from every direction at once. The weight of the water above the Galathea floor, all 10.5 kilometers of it, creates a force that has no comfortable analogy in ordinary life. It is not the weight of something heavy placed on top of you. It is pressure arriving from everywhere at the same time, looking for any opening, any weakness, any empty space. And the first thing it does to empty space is remove it. This is the environment we are going to spend the next 2 hours understanding. Not just its depth, not just its pressure, but what lives there and how and why, and what it connects to in the wider world above it. Researchers who send instruments down to these depths sometimes attach styrofoam cups to the outside of the submersible frame. Before a deep dive, it has become something of a tradition, almost a ritual. The cups go down as cups, ordinary, about 9 centimeters tall. They come back the size of a thimble. Nothing dramatic happened to them. There was no explosion, no shattering, no violence. A styrofoam cup is approximately 95% air by volume. The foam matrix is mostly void. Tiny pockets of nothing, surrounded by thin polymer walls. As the submersible descended and the pressure increased with every meter, those pockets were quietly removed. The polymer walls collapsed inward. The structure found its new, smaller configuration and held it. The cup did not break. It simply became a different cup. A much, much smaller one. When the expedition scientists attached them and retrieved them, they were sending a message to themselves about the environment. A reminder, written in shrunken polymer, of what they were descending into. The cup is the most honest illustration of the Galathea floor that exists. A world where emptiness is not permitted. Here is something that tends to surprise people when they first encounter it. We have better maps of the surface of Mars than of the deep ocean floor. Mars is tens of millions of kilometers away at its closest approach. The Galathea Deep is 11 kilometers down. In our own ocean, on our own planet. The reason is not lack of effort. It is physics. Mars can be mapped from orbit using radar and cameras. Electromagnetic radiation, radio waves, visible light, radar, travels easily through the vacuum of space. It reflects from solid surfaces and returns to the instrument that sent it, carrying information about what it bounced off. This is how we have mapped the entire surface of Mars in detail. Along with the Moon, Venus, Mercury, and the moons of Jupiter. Radio waves, the kind that carry every wireless signal we rely on, dissolve in seawater almost instantly. Not weaken gradually. Dissolve. The ocean is electrically conductive. When an electromagnetic wave tries to travel through a conductive medium, the medium generates currents that drain the wave of its energy. In seawater, this happens within centimeters. The entire electromagnetic toolkit that lets us see distant planets from billions of miles away becomes useless. The moment it touches the surface of the ocean, the deep sea can only be mapped acoustically. With sound. And sound, while it travels remarkably well through water, creates its own complications in the steep geometry of a deep trench. The walls of the Philippine Trench angle inward at sharp degrees. Acoustic pulses sent downward bounce off those walls and return with distorted timing. The shape of the trench creates shadow zones, regions where the geometry of the basin blocks the sound from returning cleanly, leaving portions of the floor effectively invisible to our instruments. We do not have a complete map of the Galathea floor, not because no one has tried, because the ocean has been, so far, uncooperative. A research submersible descending to the Galathea floor takes between 3 and 5 hours to reach the bottom. Not because the distance is unusual. 11 kilometers is a drive of a few minutes on a highway, but because the pressure builds with every meter of descent. The vehicle needs to descend slowly enough for its seals, its housings, its electronics to equalize properly. Rapid descent at these pressures is how you lose a vehicle. The pace is set not by ambition, but by physics. And the communication problem is just as challenging as the descent. Because radio does not work, everything at depth must communicate in sound. Acoustic modems can transmit data through the water column. But the bandwidth they can achieve, the amount of information per second, is a tiny fraction of what we take for granted above the surface. A high-definition video stream requires about 5 million bits per second. The acoustic data link to a vehicle at hadal depth can carry 5 to 10,000. The scientists directing operations at the Galathea floor make irreversible sampling decisions based on a data stream that would have felt slow in the early days of the internet. The picture they are working from is partial. The decisions they make are permanent. The Galathea expedition returned from its 2-year voyage in 1952. It brought biological specimens collected from below 7,000 meters. Sea cucumbers, polychaete worms, crustaceans, living things, pulled up from a depth where the scientific consensus had firmly predicted nothing could survive. There was a theory in the scientific community at the time. the azoic hypothesis, which held that the deep ocean was essentially lifeless. The pressure was too great, the cold too severe, the darkness too total. The chemistry of life, it seemed reasonable to conclude, could not function under those conditions. Edward Forbes, the Scottish naturalist who proposed it in the 1840s, was working from the best observations available to him. He was wrong, but not carelessly wrong. He was wrong because the instruments to go deeper simply did not yet exist. The Galathea expedition created those instruments. And when the specimen jars came back with animals in them, the azoic hypothesis did not survive the voyage. The organisms did. Spend time with deep-sea footage, the kind that comes back from cameras attached to landers at hadal depths, and you notice something unexpected. It is calm, not quiet in the silence of space sense, because the ocean is full of sound. But visually, strangely, it looks peaceful. The sediment drifts undisturbed. Creatures move slowly, conserving energy with every gesture. The camera light illuminates a small circle of floor, and the rest is absolute darkness. That darkness has a quality to it that surface night does not. Surface night has gradients. The glow of the horizon, the suggestion of distance, light pollution bouncing off clouds, the moon. Even in a genuinely dark room on land, your body senses the presence of nearby walls and windows. At the Galathea floor, there is no horizon. There is no distance. There is the circle of light from the camera, and then, immediately, nothing. The darkness is not a background. It is the entire context. It is what the environment is made of. And it is not new. The Galathea floor has not seen sunlight for longer than our species has existed. Longer than the mammals have existed. Since long before any vertebrate walked on land. The darkness at this depth has been permanent, uninterrupted, total. The organisms living there did not adapt to darkness. They were born into a lineage that has never known anything else. The temperature at that floor sits between 1 and 2 degrees Celsius, just above freezing. And this is not a recent condition. It is a permanent one. The water at the Galathea floor moves so slowly through the deep ocean circulation system. It may have last touched the surface before Columbus sailed. Cold water, dense, heavy, carrying the chemistry of the polar surface where it formed, sinks near the poles. It drifts through the abyssal depth over decades and centuries, following the thermohaline circulation of the ocean in a loop so slow and so vast that it defies easy imagination. By the time it arrives in the Philippine Trench and settles on the floor, it has been traveling for so long. Its connection to the surface world is almost theoretical. That water, sitting on the Galathea floor at 1 degree Celsius, was once ocean surface. It once touched the atmosphere. It once felt, in whatever sense water can feel anything, the difference between air above and water below. Now it sits 11 kilometers down in the dark. And its journey back to the surface will take longer than any human civilization has existed. Cold, dark, still, and under a pressure that would reduce the building you are in to rubble. The engineering problem of reaching this environment begins with a single architectural fact. Hollow things collapse. A steel structure with any air inside it is, at the Galathea floor, a structure under continuous siege. The pressure is not pressing down from above the way weight normally does. It arrives from every direction at once. Above, below, from every side simultaneously. It is looking for the geometry that gives it maximum advantage. In any shape with corners, the force concentrates at those corners. The edges and seams of a cylinder are under more stress than the middle of its walls. A cylinder at sufficient depth fails at its ends. The shape that resists this most effectively is the one with no corners, no edges, no preferred direction of failure. The sphere. A sphere distributes the incoming load perfectly across its entire surface. There is no weak point, no place where the pressure has more leverage than anywhere else. This is why submersible pressure hulls are spheres. Not because it is traditional, not because it looks good, because the physics leaves no better option. And the material matters as much as the shape. Standard steel, even good naval-grade steel, has a yield strength that reaches its limit. Somewhere around 600 to 750 atmospheres for a vessel of practical size. The Galathea floor delivers 1,100. Titanium, specifically a particular alloy with added aluminum and vanadium, offers higher strength for its weight. And something equally important, it does not corrode in seawater. Steel in the ocean is in a continuous electrochemical battle against the water around it. Titanium forms a passive oxide layer that is, for all practical purposes, inert. It does not rust. It does not weaken over years of immersion. The titanium sphere in the submersible that reached the Galathea Deep in 2021 had walls 90 millimeters thick. That is not a conservative estimate or a safety margin chosen from caution. That is the minimum number the calculation returns. Start with the target pressure. Set the margin you need for safety. Solve for the thinnest wall that the physics will allow. The answer was 90 millimeters. Nothing thicker. Because every extra kilogram of hull is a kilogram not available for the science. The sensors, the sample containers, the batteries, the manipulator arms. In deep-sea engineering, the minimum viable solution is the most honest statement of what the problem actually requires. In January 1960, a Swiss engineer named Jacques Piccard and a U.S. Navy lieutenant named Don Walsh descended in a vehicle called the Trieste toward the Challenger Deep. The Trieste was a bathyscaphe, a type of deep research vessel whose design used the weight of iron shot for ballast and gasoline for buoyancy. Designed specifically for one thing: going as deep as possible and coming back. It had no propulsion to speak of and very little maneuverability. It was essentially a highly engineered way of falling to the bottom of the ocean and then floating back up. At approximately 9,000 meters, both men heard a sound inside the cabin. The kind of sudden sharp crack that makes you stop everything you are doing. They stopped, checked every system, found nothing critical, resumed the descent. At the surface, hours later, after they had successfully reached 10,916 meters, the deepest point ever touched by humans at that time, and returned safely, they found the source. One of the plexiglass viewing ports, 12.5 centimeters thick, had cracked. The crack had not propagated to failure. The geometry had held. The window was damaged, but the hull remained intact. That sound, inside a steel vessel at 9,000 meters, is one of those details that does something to your sense of scale. Both men heard it and kept going. The judgment that everything was still safe, made in the darkness of the deep ocean with limited instruments and imperfect information, turned out to be correct. But the reason modern vehicles no longer use acrylic viewports is because of moments like that one. They use borosilicate glass seated in conical mounts, designed so that increasing pressure actually pulls the viewport more tightly into its seat. The Trieste's cracked window became a lesson written into every subsequent design. In May 2014, an unmanned research vehicle called the Nereus was operating near 10,000 meters depth in the Philippine Trench, southwest of the Philippines. Contact with the surface vessel was lost. The vehicle did not surface on schedule. Recovery operations located debris spread across the seafloor. The Nereus had imploded. Most people understand explosion from a lifetime of movies and sound effects. A rapid outward release, a boom, a shockwave moving away from the center. Implosion is the mirror event, and it is in some ways stranger. When a pressure housing fails under the load of 1,000 atmospheres of external hydrostatic pressure, the surrounding ocean does not wait patiently outside a door. It enters the collapsing void with a velocity governed by the pressure differential. At 1,000 atmospheres, that velocity is not gentle. The walls of the failing structure accelerate inward toward the center, at speeds approaching the speed of sound in steel. The entire event, from first failure to complete destruction, happens faster than the signal of it can travel through water to the surface. By the time any instrument at the surface could register the event, it was already over. The debris field from the Nereus covered several hundred square meters of seafloor. Post-incident analysis identified the probable failure in a buoyancy material made of hollow glass microspheres embedded in an epoxy matrix. Each microsphere its own tiny hollow structure with its own collapse depth. As the vehicle descended below its rated operational depth, microspheres began failing in sequence. Each failure increased the load on adjacent ones. The cascade accelerated. The buoyancy section lost structural integrity, and the rest followed immediately. The Nereus had been rated to 11,000 meters. It failed at 9,990. This is not a story about a design flaw or a preventable mistake. It is a story about where the edge of the physically possible actually sits, and about how precisely the ocean enforces it. The darkness has a second consequence beyond what it means for organisms living there. It shapes how we study the place at all. Radio waves cannot travel through seawater. Everything at depth communicates in sound. And while sound travels extraordinarily well through water, signals can carry for thousands of kilometers along certain pathways in the ocean. The specific geometry of a deep trench creates acoustic complications. The sound velocity in seawater depends on three interacting factors: temperature, salinity, and pressure. Temperature decreases as you go deeper, which slows sound. Pressure increases, which speeds it up. At a certain intermediate depth, roughly 600 to 1,200 meters in the Pacific, these two affects balance, creating a minimum in sound velocity. Below that depth, pressure wins and sound accelerates again. This minimum creates a natural waveguide, a channel where sound is trapped and can travel enormous distances. But signals traveling upward from the Galathea floor must cross this channel. And at the boundary, their timing is altered. Sonar mapping calculates depth from acoustic travel time. Alter the timing, and you alter the calculated depth. The corrections are well understood in general, but in the specific geometry of a narrow, steep-walled trench, the corrections become imprecise. Some acoustic paths from the floor return clean signals, Others do not return at all, bent away by the walls or absorbed by sediment at angles that do not allow clean reflection. The result is a floor we cannot fully see. Portions of the Galathea Basin remain unmapped by any current instrument, not because of lack of effort, but because the physics of the environment itself prevents the signal from coming back. All of which raises the question that has been building since the beginning. The question that the Galathea expedition first put on the table, and that biologists have been working on ever since. How does anything survive here? Not just tolerate the conditions, not just barely persist on the edge of death, actually thrive in populations large enough to sustain themselves across millions of years of evolution, developing adaptations sophisticated enough that their biochemistry runs differently from anything at the surface, shaped specifically for an environment that should, by all surface world logic, be fatal. The answer begins with pressure, but it does not end there. Before the Galathea expedition returned, the scientific consensus about the deep was shaped by a hypothesis that seemed entirely reasonable. The azoic idea that water below a certain depth was lifeless derived from logical inference. Pressure would disrupt biochemistry. Cold would slow it toward nothing. Darkness would remove the energy source that powered everything. It was not careless thinking. It was the best thinking available. The problem was the assumption at its center. That life could only do what it does at the surface. That pressure was a wall rather than a condition. That darkness was an absence rather than an environment. The specimens in the Galathea expeditions, sample jars, destroyed that assumption. And what followed in the decades after, as more expeditions visited Hadal depths, as sampling technology improved, as researchers began studying not just what organisms lived there, but how their biochemistry worked, has turned out to be one of the more genuinely strange and beautiful stories in biology. The first question about any ecosystem is always where the energy comes from. At the surface, the answer is sunlight. Photosynthesis, the conversion of solar energy into organic compounds, the foundation of almost every food web on the planet. At 10,540 meters, sunlight has never arrived. The answer has to be something else. At the surface, the ocean is alive in ways that are easy to miss. Trillions of microscopic organisms, phytoplankton, zooplankton, the entire community of the sunlit zone, live and die in a continuous cycle. When they die, they sink. What falls is called marine snow. A constant, slow, fine rain of organic particles descending through the water column. Dead cells, fecal pellets, shed mucus threads, fragments of larger organisms. All of it drifting downward, being consumed layer by layer as it falls, but never entirely consumed. What reaches the Galathea floor is the residual, the fraction that survived the long journey down through all those hungry layers. Roughly 0.5 gram to 2 grams of organic carbon per square meter per year. That is an amount so small, it is difficult to visualize properly. Imagine the caloric content of a pinch of dried leaves, spread across the area of a small bedroom, delivered over an entire year. That is the food budget for everything that lives at the Galathea floor. Every organism there, every amphipod, every bacterial community, every slow-moving sea cucumber is running on this. Which means that everything about their biology has been shaped over millions of years to operate on almost nothing. Metabolisms that would be considered inefficient at the surface are not inefficient down there. They are perfect for the available resource. Occasionally, the budget changes suddenly. A large whale dies somewhere in the Pacific. Over the weeks following its death, the carcass slowly descends through the water column. A 40-ton blue whale delivers roughly 2,000 kilograms of organic carbon to the seafloor as a single event. In terms of energy, this is equivalent to thousands of years of normal marine snow input arriving at once. What follows is extraordinary. Within months, mobile scavengers arrive and begin stripping soft tissue. Hagfish, sleeper sharks, amphipods capable of detecting the chemical signal and traveling toward it from remarkable distances. Consumption rates at documented whale falls reach 40 to 60 kilograms per day at peak activity. The whale disappears, piece by piece, into organisms that carry its energy upward through the food web. Then the enrichment phase. Polychaete worms and crustaceans colonize the exposed bones and enriched sediment around them, feeding on the bacterial mats forming in the nutrient plume. This phase lasts years. Then something stranger still. Bacteria metabolizing the lipids preserved inside the whale bones release hydrogen sulfide. Around the skeleton, a chemosynthetic community establishes itself. Organisms that derive energy from chemical reactions rather than from organic carbon or sunlight. This community can persist for decades around a single skeleton. A single whale fall can sustain a distinct biological community for longer than many of the individual organisms in it will live. The deep ocean has found ways to make almost nothing go an extraordinarily long way. But the food question is separate from the pressure question. And the pressure question is where the biology becomes genuinely strange. Every cell in every living organism contains proteins. Large molecules that fold into precise three-dimensional shapes and perform specific functions. The folded shape is everything. An enzyme that catalyzes a chemical reaction does so because its active site has exactly the right geometry. A particular pocket in its three-dimensional structure. The right orientation to hold the reactant molecules in place. Change that geometry even slightly, and the reaction does not happen. The protein stops working. The cell's chemistry fails. Hydrostatic pressure unfolds proteins. It does this by disrupting the thermodynamic balance that holds the folded structure together. At surface pressures, this effect is negligible. The forces holding a protein folded are much stronger than the tiny pressure differential under normal atmospheric conditions. But as pressure increases, the balance shifts. At several hundred atmospheres, many surface organism proteins begin losing their shapes. At 1,100 atmospheres, ordinary protein chemistry cannot maintain itself. And yet the Galathea floor is inhabited. The fish that live near the upper reaches of the Philippine Trench, and the invertebrates and microbes deeper still, have functioning proteins. Their cells work. Their enzymes catalyze reactions. Their muscles contract. Their membranes maintain gradients. Their entire biochemistry operates at pressures that would reduce a surface organism's proteins to disordered tangles. How? The answer is a molecule called TMAO, trimethylamine oxide. In shallow fish, it is unremarkable. It shows up as a metabolic byproduct, helping regulate the balance of water inside and outside cells. But in fish living at depth, it serves an additional function, one that only becomes necessary below, about 1,000 meters. It acts as a molecular counterweight to pressure. The mechanism is subtle. TMAO does not bind directly to proteins and physically hold them together. Instead, it modifies the properties of the water surrounding the protein in a way that makes unfolding thermodynamically costly. Specifically, TMAO tends to be excluded from the immediate layer of water in contact with the protein. This exclusion means that when pressure tries to unfold the protein, exposing more of its surface to the surrounding water, the system resists. Because an unfolded protein has a larger surface, and more surface means more contact with the TMAO-containing water. And that contact has an energy cost the system would rather avoid. The result is that TMAO acts as a kind of invisible pressure suit, keeping proteins in their folded functional configuration under conditions that would otherwise destroy them. Think of it as the organism adjusting its own internal chemistry to counteract an environmental force. Not with armor, not with mechanics, but with molecules. The deeper the fish lives, the more TMAO its tissue contains. The scaling is remarkably consistent, roughly 35 to 40 millimoles per kilogram per 1,000 meters of depth, as if the organism took a reading of the depth and adjusted its chemistry accordingly. But there is a ceiling. TMAO cannot be added indefinitely. At very high concentrations, it creates its own problem. It makes the fluid inside cells too concentrated relative to surrounding tissue, which draws water outward through the cell membrane. This is osmotic stress, a kind of progressive cellular dehydration. The concentrations of TMAO required to counteract pressure at depths below approximately 8,400 meters tip into the range, where the osmotic damage begins to outweigh the pressure protection benefit. Below approximately 8,400 meters, there are no vertebrates, no fish. The deepest confirmed fish ever recorded anywhere on Earth is a snailfish called Pseudoliparis bellievi, found at 8,336 meters in the Mariana Trench. Small, pale, gelatinous, translucent. It has no swim bladder, a gas-filled organ that would compress and fail at depth. Instead, it achieves neutral buoyancy through tissue chemistry alone. A combination of TMAO, wax esters, and specialized lipids, whose combined density approximates the surrounding water. Its eyes are reduced but not absent. They retain some function, enough to detect bioluminescent flashes from nearby organisms. But the full energetic cost of high-acuity vision has been stripped away. Its TMAO concentration sits just below the osmotic ceiling. It lives at the very edge of where vertebrate biochemistry remains viable. Below that line, at the depths of the Galathea floor, the floor belongs to organisms that do not face the same constraints. Invertebrates, microbes, single cells, creatures whose biology operates under rules that the TMAO ceiling does not apply to. Among the most abundant animals at the Galathea floor is a small crustacean called Hierndellea gigas. Shrimp-like, about 2 to 3 centimeters long, unremarkable in appearance. Send a baited trap to the Galathea floor and leave it for a few hours. When you retrieve it, the trap is likely full of thousands of them. They arrive in swarms at bait, arriving from distances that suggest their chemical sensing is extraordinary. In the ecosystem at this depth, an ecosystem running on fractions of a gram of carbon per square meter per year, they represent a remarkable success. What makes Hyrndalea gigas genuinely strange is its exoskeleton. The shell contains aluminum fluoride complexes, not traces, compounds. Aluminum. Aluminum is toxic to almost every known living thing. Plants spend significant metabolic energy to exclude it from their tissues. Animals that accumulate it in significant quantities typically suffer neurological and physiological damage. The entire history of biology knows almost nothing that uses aluminum as a structural material. And yet here is an organism that incorporates it deliberately into the shell that defines its body. Why is one of the genuine open questions in deep-sea biology. The working hypothesis is that at hadal pressures, aluminum compounds may reinforce the exoskeleton in ways that calcium carbonate cannot manage under sustained extreme compression. Calcium carbonate is the material most crustaceans use. But the biochemical pathway that would allow this has not been identified. The mechanism by which Hyrndalea gigas handles what should be a toxic accumulation remains unknown. No one has grown this organism in a lab under controlled pressure conditions. No one has traced the chemistry. The aluminum is there. The explanation is not. That is not a failure. That is the correct state of a genuine frontier. Then there are the xenophyophores. These are foraminifera, single-celled organisms. One cell, not a colony. They can reach 20 centimeters across at hadal depths. 20 centimeters. A single cell the size of a small apple or a large orange. At the surface, a cell that size would rupture from its own internal pressure differential. The difference between the chemistry inside and the solution outside would force water in through the membrane until the cell simply burst. But at the Galathea floor, the enormous external pressure of the surrounding water creates a different balance entirely. The same force that would implode a steel sphere and shred a synthetic rubber seal actually helps hold the xenophyophore together. Pressure in this context is not destroyer but structure. The environment that should make large single cells impossible is the environment that permits them. The xenophyophore builds a kind of shell around itself from sediment particles. Mineral grains from the seafloor, pressed and cemented into a protective test. Some species concentrate heavy metals from the surrounding sediment at levels orders of magnitude above what the environment itself contains. Lead germanium radium, accumulated inside the organism's structure at concentrations that would be severely toxic to most surface life. Whether this is a metabolic strategy, sequestering toxins to prevent damage, or simply a passive consequence of the organism's sediment handling, researchers are still working out. They are, in their way, one of the most quietly extraordinary things on this planet. A single living cell, visible to the naked eye, persisting in darkness and pressure at the bottom of the Philippine Sea, doing something that the laws of surface biology would say cannot be done. Most creatures in the deep ocean, roughly 76% of species in some surveys, produce bioluminescence. They make their own light. The chemistry of it is the same in principle, whether it happens in a firefly on a summer night or an anglerfish at 3,000 meters. A molecule called luciferin is oxidized by an enzyme called luciferase. In that reaction, a photon is released. The light is produced without heat. Cold light emerging from living tissue in total darkness. But the deep-sea version of this chemistry has been modified by millions of years of evolution. Under conditions nothing like the surface. Luciferase enzymes at depth work at temperatures just above freezing, a condition that would slow a surface enzyme nearly to a stop. Over millions of years, the molecular architecture of these enzymes has evolved to maintain catalytic activity in the cold, greater conformational flexibility, different electrostatic interactions at the active site, a looser structure that keeps functioning at temperatures where surface enzymes would seize. It is the same adaptation we see across the entire enzyme portfolio of hadal organisms. Every protein that needs to work at 1 or 2 degrees Celsius carries this same molecular signature of cold tuning. Here is the detail that tends to stay with people. The light these deep-sea creatures produce is a very specific shade of blue-green. The peak emission wavelength sits around 470 to 490 nanometers. And that is almost exactly the wavelength that travels farthest through deep seawater. Seawater absorbs most colors of light quickly. Red within a few meters of the surface, then orange, then yellow, then progressively shorter wavelengths. Blue-green persists the longest. It is the color that the ocean most willingly transmits. Millions of years of evolution, working independently and without any awareness of the physics, arrived at the precise color that the medium permits. The biology found the physics and matched it exactly. The light that living things make at depth, and the light that the ocean allows to travel. They turned out to be the same light. Whether this is coincidence or direct selection is actually an interesting question. If the organisms that produce light at slightly different wavelengths are less visible to other organisms that evolve to detect blue-green, they leave fewer offspring. The selection pressure toward the optimal wavelength is direct and strong. It has been operating for a very long time. The result is a community of living things in the dark, all speaking in the same narrow band of color that their environment was always going to favor. There is one more category of deep-sea life that inverts the entire framework we have been working within. Some microbes at hadal depths are not merely tolerant of high pressure. They prefer it. Return them to surface conditions and their chemistry slows. Not because they are damaged, but because they are operating below their optimum. Their enzymes were built to run at several hundred or several thousand atmospheres. The deep ocean is not the hostile environment they are enduring. It is home. The surface is the place that is hostile to them. For these organisms, the Galathea floor is not extreme. It is normal. This small fact has a large implication. The concept of an extreme environment is always defined relative to the observer. For every organism alive today, evolution has shaped it for the conditions where it lives. The deep sea has been selecting organisms for its specific physics for longer than most of the ecosystems we consider ordinary have existed. The sediment on the Galathea floor is a different kind of story. Not biology, but memory. Sediment accumulates continuously. Marine snow, volcanic ash carried by deep currents, mineral particles, biological fragments. The compressed remains of organisms from the water above. Layer upon layer, compressed under its own weight. Each stratum a record of conditions in the ocean and atmosphere at the time of its deposition. The anoxic chemistry of the deep sediment slows microbial decomposition. The cold slows chemical reactions that would otherwise degrade organic compounds over time. The stable pressure prevents the physical disturbance that erases shallower records. The near absence of burrowing organisms at hadal depths means the layers are not mixed by biological activity. They stay where they were deposited in sequence with fine resolution. The record goes back an extraordinary distance. 66 million years ago, an asteroid struck what is now the Yucatan Peninsula in Mexico. The Chicxulub impactor, roughly 10 kilometers across, vaporized rock. It sent an enormous cloud of material into the atmosphere. Iridium platinum group elements, shocked quartz, soot from global fires. This material settled across the entire planet over months and years, depositing a thin, chemically distinct layer on every contemporaneous seafloor. That layer, the KPG boundary, marking the end of the Cretaceous and the beginning of the Paleogene. The mass extinction that ended the non-avian dinosaurs. It is preserved in the sediment of the deep Pacific. It sits there, 66 million years old, undisturbed, readable. A thin line of iridium and shocked quartz. The signature of a catastrophe that reshaped the entire trajectory of life on Earth. Sitting quietly on the floor of the Philippine Sea. The sediment is also a seismograph. When a large earthquake occurs along the Philippine Trench system, it destabilizes sediment on the steep trench walls. That sediment slides. A turbidity current. A submarine landslide. It deposits a distinct, coarser layer across the trench floor. Each major earthquake leaves a line in the sediment record. The 1976 Morro Gulf earthquake, magnitude 7.9, more than 5,000 people killed, tsunami striking the Mindanao coast, is there. A specific stratum. Identifiable, datable, legible. You can read its magnitude from its thickness. You can read its timing from the chemistry of the surrounding sediment. A catastrophe that happened within living memory is recorded on the floor of the ocean. Permanently, in layers of displaced sediment. The most extreme, least visited place on Earth is also one of its most complete geological archives. And almost none of it has been read. Now the frame widens. The Galathea Deep is not a permanent feature of the planet. It is a stage in a process. The same mechanism that created it, the Philippine Sea Plate descending beneath the Philippine Mobile Belt, is also the mechanism that will eventually eliminate it. At the current convergence rate of 7 to 8 centimeters per year, the floor of the trench is moving. The sediment that has been accumulating for millions of years is in transit. On a geological timescale, the archive is being consumed. The oceanic crust descending into the mantle carries three things with it. The rock of the seafloor itself, the sediment resting on top of it, and the water chemically bound into its minerals. As this material sinks and heats, the water is released. Released water lowers the melting point of the rock above. Magma forms. It rises through the overlying crust and erupts at the surface. The volcanoes of the Philippine archipelago, Pinatubo, Mayan, Taal, are where this process emerges. They are, in a direct physical sense, the surface expression of what happens to the material subducted at the Galathea Deep. The organic carbon buried in the trench sediment, the compressed record of millions of years of ocean productivity, will eventually return to the atmosphere as volcanic gas. The Galathea Deep and the volcanoes above the Philippines are not separate features of the landscape. They are one connected system. That connection matters more immediately than the carbon accounting does. The Philippine archipelago is home to roughly 115 million people. The Visayas, Mindanao, Eastern Luzon, These are coastlines directly exposed to the tsunamis that the Philippine Trench system can generate. The 1976 Morro Gulf earthquake, which killed more than 5,000 people, was a product of this same geological boundary. Larger events are possible. The geometry of the subduction zone, steeper than the Mariana Trench, with a different pattern of stress accumulation, creates specific risks for specific coastlines. The sediment record at the Galathea floor contains the earthquake history of this system. Turbidite layers, read in sequence, give an estimate of earthquake recurrence intervals, how often the system produces its largest events. This is information that exists nowhere else with the same temporal depth and the same specificity. It cannot be inferred from surface geology. It cannot be extracted from satellite data. It is written in the sediment at the bottom of the trench, waiting to be read. Reading it could, in time, improve tsunami early warning systems for the coastlines that need it most. The sediment might know something about the future of these coastlines. We have barely begun to ask it. There is also the carbon question. Quieter, longer in its implications, but genuinely significant for reasons that go far beyond the trench itself. The deep trench floors of the world, including the Galathea Deep, bury organic carbon at a rate disproportionately high relative to their small area. Carbon sinks as marine snow, settles on the trench floor, gets compressed into sediment, and stays there for geological time, until subduction eventually returns it to the mantle and, millions of years later, to the atmosphere. On any human-relevant timescale, this is a one-way valve. Carbon goes in. It does not come back out within any time frame that matters to us. How much carbon is moving through this system at the Galathea Deep specifically, and how that might change as the upper ocean warms and surface productivity shifts, has never been directly measured. It is estimated from indirect proxies. It is a variable in the climate equations that policy discussions depend on. And it carries real uncertainty. The uncertainty is not dramatic. It is not the kind of thing that changes headlines. But it is real. And it is there. And it sits in the background of every serious model of the ocean carbon cycle. The Galathea Deep does not appear in climate policy discussions. It is nonetheless a participant in climate. Let me tell you what we do not know about the Galathea Deep. Not as a list, as a feeling. Below 8,400 meters in the Philippine Trench, no fish has been confirmed. But the sampling at that depth gradient is sparse. Baited camera deployments scattered across an enormous area, catching hours of footage at specific locations, missing everything between. The absence in the data may reflect genuine biological absence, or it may reflect a camera that was never in the right place. We do not know. The aluminum in Hyrndalea gigas's shell has no biochemical explanation. No pathway has been identified. No lab culture under maintained pressure has been achieved. The chemistry is there. The explanation is not. We have been looking at this organism since the 1950s, and the question has not closed. Environmental DNA surveys of the Galathea water column have returned genetic sequences with no match in any existing database. These could represent undescribed species. They could represent undescribed phyla, entire branches of the tree of life with no names yet. No representatives yet brought to the surface for study. Or they could be sequencing artifacts. We do not know. The chemosynthetic communities, organisms fed by fluids seeping up through fractures in the subducting plate that may or may not be present on the Galathea floor have not been systematically surveyed. We have hints from related systems elsewhere. We have no direct characterization from this trench. The organic carbon burial rate, how much carbon the Galathea system is actually removing from the ocean each year and locking into sediment, is estimated from indirect measurements at other trenches and scaled by inference. A direct time series measurement at this site, sustained over at least a year, has not been done. The number that enters global carbon models is a proxy for a measurement that has never been made here. And there is a more fundamental category of unknown. Researchers have collected environmental DNA, fragments of genetic material shed by organisms into the water and sediment, and found sequences that belong to nothing in any database. Not to any described species, not to any described genus, family, order, or class. Sequences whose nearest relatives suggest they belong to lineages that have been evolving in isolation, at depth, for long enough that their DNA looks like nothing else on Earth. They might be organisms, they might be artifacts, but the ocean at this depth has been running its own evolutionary experiment for hundreds of millions of years, in conditions that nothing at the surface ever experienced. And the idea that everything living there is already known, already named, already understood seems unlikely to be true. None of these unknowns require a breakthrough in physics or biology to resolve. They require sustained access to a place that is genuinely difficult to reach, genuinely expensive to visit, and genuinely rare in the scientific literature. The door is open. We are standing in the entrance, looking into a room whose far wall we cannot yet see. And the room is very large. The Galathea Deep has been there for tens of millions of years. It received its first human visitors, in any form with any instrument, only within the span of living memory. The expedition that named it sailed in 1950. The first successful descent to Hadal depths anywhere on Earth happened in 1960. The submersible that reached the Galathea floor most recently did so in 2021. In the long history of this trench, human presence has amounted to a few hours, distributed across a handful of expeditions, touching a tiny fraction of a floor that extends across hundreds of square kilometers. The organisms living there have been adapting to these conditions for far longer than we have been aware they exist. The TMAO molecule in the tissues of Hadal fish has been scaling with depth for at least as long as vertebrate life has existed in the ocean. Hundreds of millions of years of selection, working on a chemistry that we only identified and named in the last few decades. The xenophyophores sitting on the Galathea floor in the dark belong to a lineage older than most of the animals visible to the naked eye on land. The bacteria in the sediment below the floor are conducting chemistry that has been running without interruption since before the dinosaurs. The bioluminescent flashes of light that pass between organisms in the dark, those blue-green photons traveling the wavelength that the ocean allows, those are conversations that were happening at this depth long before the first hominid stood upright. We arrived recently. We brought instruments that barely survived the journey. We stayed for hours. We came back with questions. That is as it should be. The questions are the whole point. Consider what we have covered over the course of this. A name that comes from a Danish ship. A pressure of 1,100 atmospheres, derived rather than estimated. A styrofoam cup reduced to the size of a thimble. A titanium sphere whose walls are exactly as thick as the physics requires. No more. Two men who heard a sound like a rifle shot at 9,000 meters and kept going. A vehicle that imploded faster than the signal of it could travel to the surface. An organism that incorporates a toxic metal into its shell for reasons we do not yet understand. A single cell the size of an apple, held together by the very force that should destroy it. Organisms whose chemistry runs better at 500 atmospheres than at 1. A whale falling to the floor and sustaining a community for decades. A thin line of iridium, 66 million years old, sitting undisturbed in the sediment. A floor moving toward the mantle at 7 centimeters per year, carrying everything with it. Each of these is a piece of the same system. The Galathea Deep is not anomalous. It is Earth operating normally. At a scale and on a time scale, that makes human presence both necessary for understanding and nearly impossible in practice. The trench predates our species by tens of millions of years. The archive at its floor will eventually be consumed by the same planetary mechanism that created the space to hold it. The window for reading it is not infinite. It is merely very long. And we are somewhere near the beginning of the available reading time, having read almost none of it. And yet the record is there. The organisms are there. The molecules are there. The sediment layers, recording the history of earthquakes and extinctions and the chemical composition of ancient atmospheres, sit undisturbed in darkness, under 1,100 atmospheres of pressure, patient in the way that geological time is patient. 7 centimeters per year, the floor moves toward the mantle. The archive moves with it. On the timescale of geology, the document is being fed, page by page, into a process that will erase it. Not dramatically, not all at once, but steadily, irreversibly, on a schedule that has been running since before our species existed, and will continue long after. We are somewhere near the beginning of the time available to read it, and we have read almost none of it. The Galathea Deep was there before Columbus, before the first human, before the first mammal walked on land. It has been there through extinctions and recoveries, through the rise and fall of entire biological eras, through ice ages and warm periods, and the slow drift of continents. The darkness at its floor has been continuous since before our lineage existed. We arrived recently. We brought instruments that barely survived the journey. We stayed for hours. We came back with questions. And the place continues, exactly as it has always continued. Cold, dark, still, under a weight that has no good comparison in ordinary life. The weight of time holds the memory of every secret that ever fell. But the Galathea Deep was not the only mystery to vanish. In the next entry, we will explore the Tonga Trench, where the fastest moving subduction zone on Earth creates conditions so extreme that even the chemical rules governing life at the Galathea Deep no longer hold. A world separated from our own by logic we are only beginning to decode.